The real revolution in machine translation began with neural machine translation, or NMT, which leverages deep learning to overcome the limitations of SMT. At its core, NMT often employs an encoder-decoder architecture. Imagine two neural networks working in tandem. The encoder reads the source sentence, processing each word sequentially and compressing its meaning into a fixed-length numerical representation called a context vector or thought vector. This vector encapsulates the semantic essence of the entire input sentence. The decoder then takes this context vector and generates the target language sentence word by word. The challenge, however, is that a single fixed-length context vector can struggle to hold all the necessary information for very long sentences. This is where attention mechanisms come into play. Attention allows the decoder, when generating each word in the target language sentence, to dynamically focus on relevant parts of the source sentence's encoded representation, rather than relying solely on the single static context vector. This selective focus is critical for handling long-range dependencies and producing more coherent, accurate translations, especially for longer, more complex sentences. It was a groundbreaking innovation that dramatically improved NMT performance. While the encoder-decoder with attention was a massive leap, a bottleneck remained: its sequential processing. Recurrent neural networks at the heart of many encoder-decoder models process words one after another, which can be slow and makes it hard to capture very long-range dependencies efficiently. This led to the development of the transformer model, introduced in 2017, which completely eschewed recurrence and convolutions, relying entirely on attention mechanisms. The transformer's architecture is built upon stacked layers of self-attention and feed-forward networks, enabling parallel processing of input sequences. At the heart of the transformer is the self-attention mechanism. Instead of attending to a separate source sequence, self-attention allows each word in the input sequence to weigh the importance of every other word in the same sequence when computing its own representation. This parallel capability is a game changer for speed and capturing global dependencies. To preserve word order, which self-attention inherently ignores, positional encoding is added to the input embeddings. Furthermore, the transformer employs multi-head attention, where multiple self-attention mechanisms run in parallel, each focusing on different aspects of word relationships. Their outputs are then combined, allowing the model to capture a richer, more diverse set of dependencies simultaneously. This parallel processing and sophisticated attention is why transformers now dominate NMT and many other NLP tasks.